All right, I'll start putting the answers up for these. If you were solving for x in number 1, well, first you would probably move the 4 over by adding 4 to both sides, and then divide everything by 3. So this is perfectly fine to write it that way. If I divided everything by 3, I could divide the x equals 4. I could divide the y by 3, which would give me 1/3 y plus 4/3. It's nice to be able to switch from one form to the other. The second form is really nice because it's sort of more like y equals mx plus b form. So if you had to graph that, you would have a slope and a y-intercept. Okay, second one, I'll do that one up over here. Again, when you're solving for x, you're really undoing the math that was there. So the very first thing I would do in the second one is I'd multiply both sides by 2. And then I'd add 5 to both sides. And finally get x by itself by dividing everything by 3. And of course, if I wanted to, I could make this 2/3 y plus 5/3. So both of these are solving for x because we've gotten x by itself. The third one. I want to get the x by itself, so I'd start by adding 5 to both sides. Divide both sides by 3 gets my x squared by itself. And how do you get rid of the squared? What's the opposite of squaring? Square rooting. And when you square root both sides, if I just square rooted both sides and wrote this, I would lose a half a mark. Does anybody know what I forgot? And it's something we always seem to like to forget when square rooting both sides.
Plus or minus.
Plus or minus. Because when you square root both sides, you have to do plus or minus. This is sometimes really hard for students, and I'll explain it here in a little bit. If you have just the square root of 9, the answer is only positive 3. Only positive 3. It's never negative 3. Your calculator, you type it into your calculator, it only gives you positive 3. But if you started with something squared equals 9, now there's 2 possibilities, right? Because 3 times 3 is 9, and negative 3 times negative 3 is also 9. So when we take the square root of both sides, I could do this, but I have to do the plus or minus because this part right here is just 3. So I need that plus or minus in front because in this case, it could be positive 3 or negative 3. So what we have to remember is if we square root both sides, there is the possibility it could be positive or negative. So the action of taking the square root of both sides requires that we add that plus or minus. And then for number 4, okay, this one looks a little bit more complicated. What I'm going to do is I'm going to think, well, here's the thing that's squared inside that green box. If that was all by itself, then I could square root both sides. So maybe I'll try to first see if I can get that item in the green box all by itself. So I'm going to subtract 4 on both sides. And then divide both sides by 3. I'm going to write this on this side. So I'm going to write the y minus 4. Divide both sides by 2, sorry. That gets that green part, right? I put a green box around it originally. I'll put a green box around it again. I got that by itself. Now, to get rid of a squared, I can square root both sides. If I square root both sides, I'd get plus or minus y minus 4 over 2. And then I could get x by itself by just adding the 3 to the other side. And I could get the x value by itself. Now there's more math we could do in some of these, like technically the square root of fraction is the square root of the top over the square root of the bottom. And you learned in grade 11 you shouldn't have square roots on the bottom of fractions, so we have ability to rationalize, but for right now, we'll just get the x by itself. What we're looking at in 3.5, the last section of this unit, is a special kind of transformation called the inverse. And so we're going to skip the construct the understanding. I'm going to get you to turn to page 237. And at 237, they have this at the top, that if you reflected in the line y equals x, and y equals x, I'll draw it right here, is this diagonal line. Straight line with a slope of 1 and a y-intercept of 0. That's y equals x. If you flip something over that line, some very cool things happen. Okay? First of all, any point that was on one, if I had, for example, the point -2, +3, and I flip straight over this line to a new point down there, what's going to happen is your x's and y's are going to flip, and they're going to switch. So anytime we reflect over the line y equals x, all we're doing is switching the x's and the y's. When this happens, we get an inverse function. Okay? And what the inverse function does is it undoes the original function. So we're going to look at this 2x plus 4 and the f inverse 1/2 x minus 2 a little bit to see how this works. And sometimes when I'm talking about functions, I actually like to draw little function machines. So this is going to be my little function machine for f of x equals 2x plus 4. For example, if you threw a 2 inside the machine, it would go in the machine, go clunk, 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 clunk. You plug in a 2, do you see that out would come an 8? Agreed? Okay. If I threw in a 4, you multiply that 4 by 2, you get 8, then you'd add 4, out would come a 12. Okay. Now I'm going to tell you that I threw in something and I forgot what it was. Okay? I forgot what I threw in, but out came a 2. Can you tell me what I threw in? Well, now you have to work backwards, right? Whatever I throw in gets multiplied by 2, and then I add 4. How would you work backwards? Well, I added 4 last, so maybe I should subtract 4 first. And then instead of multiplying by 2, I should divide by 2. Does that make sense? And then originally would have been a -1. I'm going to write that working backwards exactly as we said it. What do we want to do first? First, we said we wanted to subtract 4, and whatever answer we get, we wanted to divide by 2. Does that make sense writing it that way? If I was working backwards, I'd have to undo the 4, so first I'd have to subtract 4. And then whatever answer I get, I divide by 2. I can write that algebraically. Sometimes people even like to put brackets there to make sure that they say I did that first. First I subtracted 4, and then I divided by 2. And sure enough, if I double check this, if I throw in a 2 into this equation, 2 minus 4 is negative 2. Negative 2 divided by 2 would give me negative 1. If I threw in a 12, what's 12 minus 4? 8. 8 divided by 2, out would come a 4. Does that match up with? You see how it's undoing the other machine. And with inverses, so my original equation in blue was this. Y equals 2x plus 4. If inverses reflect over the line y equals x, and the x coordinate and the y coordinate get flipped, we can also do that in the equation and flip the x and the y. If I flip the x and the y, I would have x equals 2y plus 4. And the question is, can I now get the y by itself? And getting the y by itself is undoing what you just did. If I want to get the y by itself, what do I have to do with the 4? I have to move that 4 over. Oops, I'm going to stay black. X minus 4 equals 2y. And then if I wanted to get y by itself, I would get x minus 4 all divided by 2. Which I could write as this as well. That's how they wrote it. But I like the original one because I could really see myself undoing the function that way. Whereas if I wrote it as 1/2 x minus 2, I'm like, well, where did you get the minus 2 from? I really like seeing that you do exactly the opposite to undo. And whenever you undo something, okay, whenever you undo something, you get back to where you started from. Okay, so look at this. If I put, I'm going to erase some of these numbers. This is, and I think this will make sense to you. I'm going to put a little conveyor belt along here. Okay? Tell me a number to throw in. 5. Perfect. We're going to throw in the number 5. It's going to go into the first machine. Clink, 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 clink. What would come out? A 14. Right? That 14 would go on the conveyor belt and get thrown into here. Then it's going to go clunk, clunk, clunk. Well, what happens when I throw 14 in here? 14 minus 4 is 10. 10 divided by 2, out would come 5. I threw in a 5. The first function changed it. The second function undid it. I should get back to what I started with. That's what an inverse, whenever we do inverses, we want to undo something else. And math is all about inverses. You started in grade 1. The first math thing you learned was adding after counting. Okay, well, we counted first. But the first math operation, it's not like you got to math in grade 1 and like, okay, kids, you just learned how to count. Let's do trigonometry. No. The first thing, they're like adding. And then what came immediately after adding? The inverse of that. What undoes adding? Subtracting. And then you got a little bit more complicated. Wait, we're multiplying now. And that was a complicated thing for a bit. And then what's the opposite of multiplying? Then you learn dividing. So all along math, we have been learning functions one way. And then it's like, okay, you just learned how to square something. What am I going to teach you next? Square rooting. So we can undo it. Like, some people are like, well, if you just teach me how to do stuff and undo it, why don't you just not teach me anything? I can be just fine. Just right where I started from. Right? Life would be good, right? But we need to know how to do things and how to undo them. And that's the inverse. The inverse, you can find the equation algebraically by switching x and y. You can find things graphically by taking the points and switching x and y. And what that does graphically is it flips things over the line y equals x. And we have this new notation for a function of an inverse, f with a little -1 of x, which is confusing because it looks like an exponent. It does not, this is important, this does not, you know how a negative exponent moves it to the bottom? These are not equal to each other. It's not a -1 as an exponent, it means its own thing. And I think mathematicians run into this all the time. They only have so many symbols they want to work with, and they have so many things they want to say, that sometimes they mix up some of the, they're like, no, this is not an exponent anymore. This is an inverse, right? And with functions, if we put, like later we're going to put a little dash up there. Well, that's the derivative. Like, they keep inventing new tiny little symbols because they're lazy. Sorry, I'm lazy. We don't want to write a lot of things. So we're like, what is this tiny symbol? And then it's special code. Oh yeah, this is special code for inverse. And only if you're a mathematician do you know what that means. Or grade 12 student, now that you've learned it. So we're learning all of this little coding stuff so that mathematicians can continue to be lazy and write things as small as possible. Because really, that's part of the power of math. We take complicated things, reduce them to equations that we can work with, so we can solve things, and then take that and say, here's the answer to your thing. Because working with the real life stuff is too busy and gets too complicated. So our laziness actually has an efficiency to it. But the problem with it is it makes learning math hard. Because they take out a lot, like, here's a whole bunch of explanation. They reduce it to like, what just happened? What am I doing now? Because I'm working with something so small. Okay, so let's look at example 1 here. Here is the graph of g of x. Sketch the graph of its inverse on the same grid. So what I'm going to do here is I'm going to draw with a dotted line because it's not actually part of my graph. I'm going to draw the line y equals x. I'm going to take these 4 key points on my original graph. I'm going to label them. So this one's at -4, 4. This one is at -1, -1. Here we have 1, 3. And here we have 3, 2. I'm going to take each of those points and switch the x and the y. So on -4, -4, I'm going to now draw a dot at 4, -4. -1, -1, what happens when I switch the x and the y there? It stays at -1, -1. Does that make sense? 1, 3 is now 3, 1. And 3, 2 is now 2, 3. So I've got my 4 new points. Sometimes connecting the dot can be confusing because if you connect the wrong dots, you're going to have a problem. So a couple of ways you can do this. You can say, well, I knew these two were connected, so that means these two are connected. These two are connected, so those two are connected. Okay? You can also just use the idea of a reflection. Now, reflecting over a diagonal line is kind of hard for our brain. So I'm going to tell you, you are able to cheat on the final exam. You take your paper. No one's looking. You turn it sideways so that the diagonal line is flat. No one will notice you doing this. Flipping over a horizontal line, or if you like it up and flipping over a vertical line, that's easier for your brain. Right? If I take, well, I don't know if I can actually do this. Wow. Right, I'm going to show you how to cheat. Oh, this is not good. Shouldn't be doing this. Is it there somewhere? Oh, it's way up here.
The word, yeah.
Oh, that's not what I wanted to do. Okay, let's try that again. Select all. Oh, now it's all together. Copy. Okay, go here. Paste. Yes. There. I now turned it so that my diagonal line, and does it look like a good flip over that line? Okay, and then once you've done it, you turn your page back. No one ever noticed. And you've got your new graph. Okay? Some things that they sometimes look on the exam is they sometimes look, well, now let's turn sideways. These would be these 2 points right here. Any point on the line y equals x, that should be the one that stays the same, right? Just like we saw with the -1, -1. Flipping that x and y keeps that the same. Part B says, is the inverse a function? And this is something you've learned in previous years and most likely forgot, is something called the vertical line test. The way the vertical line test works is you draw or imagine a vertical line. There's a vertical line. And if I take this vertical line and I drag it across my red graph, do I ever hit the red graph more than once? No. There's never a place where I hit the red graph more than once. That means the red graph is a function. But right here, do you see I'm hitting the blue graph twice? In fact, right here, I hit the blue graph 3 times with my vertical line. Okay? It is not a function. Because it does not pass the vertical line test. When something does not pass the vertical line test, what that means is there are some x values with more than one y value. And this is problematic with functions. Like your calculator is one big, massive function thing. When you do 2 plus 3 and you push enter, has it ever told you something other than 5? No. Okay? When you plug something in, it always gives you the same answer. When something is not a function, this is saying, hey, right, I'm going to move my vertical line to 2 here. Oh, I'm going to try, there we go, right at 2. This is saying, you're doing some math on your calculator and you say, hey, what's the answer when x is 2? And your calculator says 3. Perfect. And a little bit later, you're like, oh, I forgot. What was the answer when x is 2? And your calculator says, oh, -3. You're like, that's not what it was last time. And the next time it tells you 0.5, you'd be like, my calculator is no longer working. It is not functioning. We use the English word for something functions or not functions. When it works, when things work, you want it to do the same thing every time, right? Can you imagine if your car was random? You put it into reverse, sometimes it goes into drive. You'd have to just like slowly, like, what is it today? You'd have to slowly, like that would, You'd be like, I don't want this car anymore. It's not functioning. It's not doing the same thing every time, giving me the same answer every time. That's what the vertical line test shows us. If it hits only one thing all the way through, then every x value has one y value and it's a function. If it doesn't, then it's not a function. And so actually there's something new you can learn called the horizontal line test. You draw a horizontal line test. And if the original red function doesn't pass the horizontal line test, it means your inverse won't pass the vertical line test. So if the original function doesn't pass the horizontal line test, your inverse won't pass the vertical line test, because horizontal lines are y equals, vertical lines are x equals. And if you just switch x and y, horizontal lines become vertical lines, and vertical lines become horizontal lines. Okay, we're going to do domain and range of both the function and its inverse. So my red graph, smallest x value was -4. I'm going to do this in interval notation. Biggest x value was 3. So my domain went from -4 to 3. And my smallest y value was -1. My biggest y value was +4. On my blue graph, my smallest x value is -1. My biggest x value is +4. And my smallest y value is -4. And my biggest y value is 3. Do you notice this? If x switches with y, do you see how the domain switched to become the range? Everything with inverses has to do with x's and y's switching. In every aspect. In the equation, in the graph, in domain and range. In lines, vertical lines become horizontal lines. X's and y's switch. And so this is the last type of transformation that we're learning. You can circle questions 4 and 9.